You stay the whole time too. Yeah. Cuts are also.
All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good to hear. All right, so today, no miscommunication today. There's no promise of guest speaker, so it's just me. So we'll be continuing on with our lecture notes. Today we're starting a new topic. So we're starting a topic called lump parameter modeling. We're gonna spend a bit of time here just because lump parameter modeling is it's a pretty cool concept. It actually has applications to fluid mechanics, obviously, and heat transfer as well. So, and if you've taken 407 before, you may have already kind of gotten a sneak peek of this before. But you know, we're going to be applying it to blood flow and fluid mechanics here today. Good afternoon. Good to hear from you. Okay. So just announcements. So the only assignment that I have out there right now is the Simvascular tutorials. Remember, that is due this Friday. So I've already gotten a chance to chat with quite a few of you, you know, mostly through emails, but some have come to office hours as well. So it seems like everyone's models are coming on pretty nicely. If you haven't had a chance to start the Simvascular tutorial, please make sure you get started on that. It is, you know, if you know what you're doing, the Simvascular tutorial, it can be done very quickly. But you know, for all of you, this is your first time, and so you know, you're going to run into issues and things like that. So make sure you give yourself enough time to do the tutorial and work on it, and you know, run into issues and ask me questions. And okay. So I have one more office hours before the tutorial is due, and that's this Thursday at 2:30 p.m. Okay, so make sure if you need some extra help, you can stop by the office hours on Thursday. If not, you can always send me an email and then we can set up an appointment to meet outside of that. Or I can just, you know, try to help you as best I can. Okay. All right. Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So like I mentioned, the topic for today is lump parameter modeling. So I'll be saying lump parameter modeling a lot today, and so you know when I write it down, I'll probably shorten it to LPM because that is much shorter to write than lump parameter model. Okay, so if you ever hear me say LPM, what I mean is lump parameter model. Okay, so let's take a step back and think about everything that we've learned so far. Right, so we've learned a lot about just fluid mechanics in general. We've learned a lot about the cardiovascular system. We've learned about how those two relate. And we've picked up on a lot of really interesting phenomenon in the cardiovascular system as well. So things like pressure wave propagation, things like Wind-Kessel models, velocity distributions, things like that. Okay. Hopefully, the one thing that I've left you with, the one impression that you should have gotten from all this is that blood flow is really complicated. Okay. First of all, the governing principles behind blood flow is fluid mechanics, and fluid mechanics, I think we can all agree, is one of the more difficult subjects that you have to learn in engineering, right? So there's that, of course, but then you have all these other kind of complexities on top of it. Deformable walls, all the biological stuff, mechanical transduction. So and when you take it all in totality, blood flow is a very, very complicated beast. And to this day, I think we're still, there's still a lot of research being done to better understand blood flow and kind of the long-term effects and how it affects things like disease and things like that. Okay. So in order to perform an analysis or in order to do any kind of useful work with a complicated subject like this, we always resort to something called modeling. So if you kind of make a career and you kind of get into more kind of research and development or analysis, modeling is a term you'll hear a lot. And it's often a term that's kind of used and not really kind of explained what people mean by that. So, a model, when people refer to a model, they're basically referring to another representation, often a mathematical representation of the complex phenomena in question. And the idea behind modeling is that, the real life phenomena or the real system is too complex to really kind of work with on its own. And so we want to give it a different representation to make it easier to work. Okay. We've already seen an example of this in this class, right? When we were talking about, pressure waveforms and flow waveforms in the cardiovascular system, we discussed the Windkessel model, right? And so just to kind of remind you, just to kind of refresh your memory, the Windkessel model was this kind of three-element system where we have on one hand, we have a pump. We have some kind of compliant, kind of flexible wall chamber. And then at the end, we have these kind of outflow microchannels. Okay. And so the idea, so when the Windkessel model was first developed in the late 1800s, this was developed by scientists to try to better understand the physiology and the fluid mechanics inside the cardiovascular system. Okay. So, ever since science kind of became it's a thing, the modeling has kind of been, a big part of that, right? Anytime you have an equation or mathematical formula that describes some kind of physical behavior, that in itself is a model because that formula is there to predict or to kind of represent a physical phenomenon, without you having to go out and actually try it. Okay. So there's all different kinds of models and all different kinds of situations. And as you can imagine, technology has since come a long way. Right? And so in today's time, a lot of models that a lot of people are interested in researching are computational in nature. So computational models, they leverage kind of the power of computers, high performance computing, to solve these equations and to give you results and to model these types of phenomenon, without actually having to go and physically measure and observe. Okay. All right. So one example that we're going to get to eventually in the final project is, a computational fluid dynamics simulation. Okay. But I don't want to get too ahead of myself. We're going to cover CFD later on in the class, but just to kind of give you a preview, what CFD aims to do is that it aims to solve the Navier-Stokes equations, using computations. Okay. So that's great, right? CFD is a very well-known model. It's used in lots of different applications, from aerospace to blood flow to pipe flow, all kinds of things. Okay. There's one issue with CFD. Okay. And I'm using CFD just as an example, but you can kind of say this about certain models in general, is that even though CFD here produces very highly accurate and very highly resolved results, it's also very difficult to perform and often very time consuming as well. Okay. And so if we kind of visualize this, right? So, in reality, there's tons of different models. This is just kind of a theoretical kind of graph here. So on the horizontal axis here, we have, I would say, cost and difficulty. Okay. And on the vertical axis, we have, let's call it accuracy / fidelity. Okay. We'll just say accuracy. Okay. I don't know why I drew negative axes. We're only going to use the top right. Doesn't make sense to have negative costs or negative accuracy. That makes no sense at all. All right. Anyway, so if I were to plot, right, and so and I will say this is not an established thing. This is kind of just my own opinion, right? CFD would probably be somewhere up here. Okay. CFD gives you a very highly accurate, a very highly resolved picture of what the fluid mechanics looks like in a particular setting, but it's just very, very costly to do. Okay. And so in a perfect world, if you had infinite resources and infinite basically computing power, you should just do CFD, right? And so because that's kind of what gives you the most accurate solution, right? But oftentimes, using a very highly accurate model like this is just not practical. It's just too costly because not everyone has access to a supercomputer. Not everyone has access to very high powered software, right? And sometimes it's overkill, right? That's the term that's often used, that using a very highly accurate model is sometimes overkill for certain applications. Okay, there's actually a lot of really interesting work, kind of in this realm of the modeling of sphere. Okay. And so models that may not be the most accurate or the most high fidelity, but they come at an extremely cheap cost. So these models right here are cheap, but not as accurate. Okay. And so you may be wondering, if a model is not as accurate, is that even useful to us, right? Is that even, if we have the technology for CFD, why are we wasting our time with some of these really cheaper models? Well, a cheap model, even though it may not give you as highly accurate or highly resolved results, can still be useful for evaluating certain things. It all really depends on what you're looking for from your model, right? So the reason I'm bringing this up, the reason I'm kind of giving you this quite lengthy kind of introduction to this is that lump parameter modeling, which is the subject for this week, is kind of in this sphere right here. And so I want to emphasize this because lump parameter modeling, it's fairly intuitive, right? There's the kind of the barrier to entry is certainly a lot lower than CFD. It's a lot easier to do. It's a lot easier to solve. Oftentimes you can solve a lump parameter model by hand, although we'll talk about how to solve it in MATLAB as well. And even though it's not going to give you as highly resolved results as CFD, it can still be really, really useful. And in fact, there's a lot of research that's actually being done to actually combine lump parameter modeling with CFD. And so you would basically use the lump parameter model as a boundary condition for your CFD model. And in fact, we're actually going to be doing that for your final project once we get to that point. Okay. All right. So I want to emphasize this, that lump parameter modeling, it's not something that's highly accurate, right? So I kind of want to make that very clear from the beginning, but it could still serve a lot of really interesting purposes, especially in a classroom setting. So especially in a setting like this where where you guys are learning kind of about cardiovascular biomechanics for the first time, there's a lot of really cool information that can be gleaned from lump parameter modeling that kind of is consistent with kind of cardiovascular biomechanics in general. Okay. So that's kind of the motivation of kind of why we're going down this path right here of lump parameter modeling, because it's a modeling technique, not as highly accurate as CFD, but it's like a starting point. Okay. All right. Any questions on this so far? Okay. All right. And so, and I like to start with lump parameter modeling. And so, we're kind of making a transition here. So we're kind of closing the chapter on the first part of the class, which is mostly kind of introduction and kind of background information on cardiovascular stuff. Now we're actually getting into the modeling and the engineering and the analysis, right? So lump parameter modeling also kind of gives us a good starting point, because as we kind of progress through the class, as we go through the next 10 weeks, we're going to work our way up the chain. So we're going to go from lump parameter modeling um, to rigid pulsed health flow modeling. That's like Wormersley profile, to deformable wall modeling. These are all 2D stuff, and eventually we're going to reach our way up to CFD. Okay, so it's almost kind of like a roadmap up to CFD, which is kind of the crown jewel of this class. Okay. Okay. So now that we kind of know kind of why we're doing lump parameter modeling, let's actually define it. All right, so lump parameter modeling, like the name implies, basically utilizes these things called lump parameters, right? So we're basically taking the biomechanics, taking the physics of the cardiovascular system, and lumping that physics into certain types of parameters. Okay? So a lot of the physical properties, a lot of the physical phenomena that we've been talking about, we're going to lump them all, or we're going to group them into certain lump parameters. Okay. In particular, the types of parameters that we're going to be looking at are circuit elements or circuit parameters. And so what we're going to be doing is we're going to be taking our blood vessels and representing them using electric circuits. Okay. All right. So let me give you a visual example. So, you know, let's say that we have a bifurcation, right? So we have a certain blood vessel, it breaks into two. Okay. So, one thing that we can do is we can model the fluid mechanics inside this bifurcation using Navier-Stokes and solve it with CFD. Okay. Or we can represent this using a lump circuit, right? So let's say that, for each branch right here, we have an inductor, a capacitor, and a resistor that models each branch. Right? So we have like this. Okay. Right. So instead of modeling the fluid mechanics in the vessel on the left, right, we're instead going to be computing the solution to the circuit. Okay. So circuits is probably the last thing you expected to use in a cardiovascular class, right? But circuits are actually really helpful, and if you've ever wondered why, as part of this major, we kind of force you to take that random mass circuits course. Circuits actually has a lot of really interesting applications, and so for those of you who have taken heat transfer already, I think at heat transfer you learned something, the concept of thermal resistance, and so this is similar, except we're going to take it to the next level. So we're going to incorporate not only resistors, but we're going to incorporate inductors and capacitors as well, and then apply that to fluid mechanics. Okay. All right. So why are we using circuits, right? So the reason we use circuits is that circuits are relatively easy to solve because you can kind of model the behavior in a circuit using ordinary differential equations. Okay. Or for short, we call them ODEs. Okay. And the thing about ordinary differential equations is that they are relatively easy to solve, right? In fact, we can solve a lot of them by hand, right? Okay. We can solve a lot of ordinary differential equations by hand. Sometimes what you'll see is that, especially for circuits, you're going to come up with a set of ordinary differential equations. So not only one, but you're solving maybe 3 or 4 or 5 ordinary differential equations simultaneously. Okay. That may be a little bit difficult to do by hand, but that's actually quite easy to do in code. And I'll show you the code and how to solve it in MATLAB. So I know at the beginning of the semester I mentioned that MATLAB will be used in this class. I know that kind of was a little bit uneasy. We're not make people uneasy, but we're not actually going to be coding or developing code in MATLAB. MATLAB has a very nice tool called ODE 45 that you can actually use to solve differential equations. So it's a particular feature in MATLAB. There is some coding involved, but it's not as intense as what you're probably thinking. And so I'll show you how to use that tool and use it to solve for these differential equations. Okay. Any questions on this so far? Okay. All right. So all this sounds great, right? And so we've we kind of motivated why we're doing this, right? This is another modeling technique. We can kind of see kind of a strategy of how we're going to do this, right? Let's talk about downsides, right? So, we've already mentioned that lump parameter modeling is not as accurate as kind of doing a full CFD or running the full Navier-Stokes, okay? So we already know that, the result that we're going to get from an LPM is not as accurate, okay? Let's kind of dive into this a little bit deeper. So the main downside or the main drawback to using LPM is that we lose basically all sense of kind of spatial information. Okay. So what do I mean by that? And so if you were to take your blood vessel here and solve for the velocity, right? We could take any location inside here and compute the exact velocity and the exact shear stress and so on, right? Whereas for a lump parameter model, right? Even though we can kind of visually see, right? So usually when we draw circuits, we usually draw them with some kind of spatial orientation like this, right? What we compute, and so let's say that we compute the pressure here, okay? Right? You would compute the pressure at a junction between a capacitor and a resistor. That's quite common, okay? When we can kind of visually see kind of where that is here, but when you're actually solving the equations, right? You're just solving for a pressure. Not only that, but you're limited to when you compute this pressure, right? We basically assume that this pressure is the same in every part right here. The only time we can experience a change in the parameters or change in the results is when we move past a circuit element. Okay, that's very different than like saying that if we start from this point 1 right here on the left, right, we can move just a little bit downwards right here to point 2, right, and we can actually compute and see that there's a change in pressure, there's a change in velocity as we move from point 1 to point 2. Okay, in lump parameter modeling, you lose all sense of space, right? You only see a change in results when you move past an element. Okay? And oftentimes, you're not going to make these circuits to have, dozens and dozens of elements. You're going to try to limit it to just a few elements. So, the main downside to using LPM is that you lose all sense of spatial information. Okay. But what you gain from this is a model that's quite easy to solve. So, I want you guys to keep that in mind as we start to get through the equations. Okay. So that's the idea of lump parameter modeling. Let's meet some of the actors. So let's meet some of the cast. Okay. So let's talk about the different circuit elements that comprise our lump parameter modeling. Okay. We're going to discuss, mathematically how to represent them, but also just kind of physically what they represent as well, because that's, if anything, that's probably the more important part here as well. Okay. All right. So in reality, lump parameter modeling goes pretty deep, and there's actually a lot of really interesting research that goes into it. And you can imagine all different types of circuit elements are employed here. So that includes the basic ones like resistors, capacitors, inductors. We have some of the more complicated ones like diodes, op amps, things like that. So all of those kind of a physical meaning. For this class, we're mostly gonna limit ourselves to the basic elements. And so the basic circuit elements are resistors, R, capacitors, C, and inductors. I never understood this, but inductors are represented by the letter L. There's no L in inductor at all. I've never understood why we use L for that. Okay. All right, so in our analysis, we're going to focus on these three here, but just know that you can add more stuff, especially things like valves and things like that. You need things like diodes to represent those, but for the most part, we're going to stick to just the large vessels and just do resistors, capacitors, and inductors. Okay. Okay, so we're going to go through each one. We're going to go through their equations, and we're going to talk about what they physically represent in blood flow. Okay. So let's start with resistors. So resistors are the most basic of circuit elements. Okay. So in terms of blood flow, okay, these represent the fact that as blood flows through a vessel, right, there are viscous friction forces that kind of resist the flow of blood. Okay. Whereas those viscous forces are going to slow down the blood flow. Okay. If you think about what a resistor does for electric circuits, it does the same thing, right? So if you have a resistor, the main role of the resistor is to slow down the electric current, right? So if you connect a wire between two places, you put a resistor in between, the resistor is going to impede or slow down the amount of current that flows through. Okay. So resistors in LPM is the same thing. So think of it as, so i.e., right? Resistors are things that are going to impede or slow down blood flow. All right. So visually it looks something like this. So let's say that we have a blood vessel here. Okay. Right. We know that if we have an internal flow like this, we have pressure-driven flow. So as long as P1 is greater than P2, okay, blood flow is going to go from left to right. So the way that we can represent this using a resistor looks like the following. So let's say that we have our resistor like this. Okay. And so our we represent the pressures as like voltages in a circuit, right? So we have a pressure drop. A pressure drop on a section of vessel is represented in LPM as a voltage drop over a resistance. So that's the main analogy that we have here. So basically, whenever you have a section of straight vessel, you can represent that in LPM using a resistor. Okay. And that resistor is going to capture all the viscous friction, all the viscous resistance forces, viscous shear forces within that section of the vessel. Okay. All right. And so we already have this connection here. So pressure drop and voltage drop are equivalent. Okay, so pressure and voltage are the same idea. The other analogy to make here is that flow rate volumetric flow rate in a fluid mechanics situation is going to be the same as electric current in this circuit. Okay. All right, so just to summarize this, let's say that we have delta P. This is equivalent to delta V in a circuit, okay? And then Q in fluid mechanics is the same thing as I, current, okay? The pressure drop, voltage drop, flow rate, with that analogy in mind, we can form an equation that relates pressure drop and flow rate. And luckily, we have a circuits equation that relates the voltage drop and the current on a resistor. Okay, so that's Ohm's law. So through Ohm's law, we know that the voltage drop on a resistance is equal to the product of the electric current flowing through the resistance multiplied by the resistance of the resistor. Okay, so we have delta V is equal to IR. I already labeled something. And so by that same token, if we use our analogy, right? So we say that pressure drop is the same thing as voltage drop, flow rate is the same thing as current, right? We can make an equivalent Ohm's law for fluid mechanics. Okay? And so what we say here is delta P is equal to Q times R. Right. And in fact, I've been working with this so long that the equation on the right actually looks more natural to me than the one on the left. Right. Even though the one on the left is the actual Ohm's law. That's the one that Ohm is famous for. I've just been working in fluid mechanics so long. The one on the right looks more natural to me. Okay. And in fact, the one on the right should be familiar to you too, because we've seen this before. If you think back to our unit on fluid mechanics review, right? We saw this exact same equation right here. And so if we took the resistance R, right? We know that resistance represents the viscous resistance of the pipe, right? And back in the fluids review, we found this to be equal to 8 times mu times L divided by pi R. Let me use little r here to not be confused. Little r is the radius here to the 4th power. So this equation here, it basically takes the geometry of a blood vessel, takes the viscosity, and computes the resistance. Right, so this concept of, relating pressure drop and flow rate in a blood vessel is we've seen it before. We've already kind of discussed this at length, a few weeks ago in this class. And so all I've done here is basically taken that concept and related to the concept of electric circuits. Okay. All right. Any questions on this so far? Yeah.
Does this also translate like well into other circuits like formulas? Like if we're to like find the power of the flow, it would be the flow rate times the pressure difference?
Yeah, yeah. So you can use the same analogy here. So anytime you see pressure drop, you can give the analogy for voltage drop. Flow rate is the same thing as current, and so you can take a lot of the equations that we develop for fluid mechanics, and then kind of find the kind of analogous equation in circuits as well. Granted, in circuits they have their own sets of equations, so it may not be exactly the same, but the relationship should be the same in terms of whether power is scaled on voltage drop squared, things like that. So you can definitely continue to draw those comparisons, but there may be like a proportionality constant that's missing for circuits. But you can kind of understand the general behavior based on this analogy.
So like for context, I guess like the relation of like current to charge would be like volumetric flow rate to volume.
Yep.
Okay.
And actually we're going to get to volume soon, because once we talk about capacitors will be dealing with charge and volume. Yeah. Mm-hmm. All right, any other questions on this so far? Okay. So for resistors, we spent a lot of time talking about resistors, but just remember that whenever you have a straight section of tubing, of pipes, right, there's always going to be some frictional power loss, and that's represented by a resistor, right? So that's all that the resistor represents. Right? And that resistance is always present. As long as you have viscosity in your flow, there's always going to be some viscous loss. Okay. The second type of element that we're going to go over are capacitors. All right, so to introduce capacitors and what they represent for fluids, let's talk about what capacitors actually do for circuits first. Okay. And so in circuits, capacitors are responsible for storing charge. Okay. And so in the sense that, sometimes capacitors get confused for batteries. And so, they're not quite the same thing. Batteries also store electric charge, batteries store electric power, but batteries store them over a long period of time. So capacitors are kind of more kind of short-term, kind of temporary kind of storage for charge. Okay. Okay. And so in LPM, okay, capacitors are used for the same thing, but if we kind of continue our analogy we've talked about before, instead of electric charge, capacitors are going to be there to store blood volume or blood in general. Okay. All right. So why do we have these, right? So what is a capacitor meant to represent? So these capacitors represent the fact that blood vessels are flexible, right? So they're flexible walls, and as such, they can kind of expand temporarily to store flow. So let's visualize this. And so, so let's say we have a small blood vessel like this, blood flow comes in, right? So we'll represent the blood flow as Q, okay? So let's say that there's a large influx of blood flow coming in. So let's say the heart just contracted, and so it's going to be outputting all this blood, right? Because of the resistance of the capillaries, right? All that blood can't rush through the entire system at once. And so what happens then is that your blood vessel is going to expand. The blood vessel is going to expand to kind of temporarily store that flow. So it has somewhere to go. Okay. All right. And so if we draw the analogy, right? We have a capacitor. And traditionally, a lot of our capacitors here are linked to ground, just because we do just mostly use them as just kind of temporary parallel storage for our flow. Okay. When charge comes in, so charge usually comes in the form of a current, electric current I, right? Some of that current is going to pass through, right? Just like, in our expansion example here, some blood is going to go through, okay? But a lot of that charge may go into the capacitor to store it, right? And so we get a situation that looks like this. And so we have our capacitor here, okay? Except now it's kind of it's stored flow or stored charge. All right. So just like we did with the resistors, let's talk about the equations that we use to model this behavior, right? So for an electric capacitor, we have the voltage on a capacitor is equal to the charge divided by the capacitance. Okay, so you have voltage. This Q here, I know it gets confusing because I'm using Q to represent flow rate, but this Q here represents electric charge. And the C here is the capacitance. Okay. So capacitance is a parameter that represents how much charge this capacitor can store. Okay. All right, so typically we don't work with this form, at least not for lump parameter models. So let's take the time derivative. Okay. So I'm going to take the time derivative of both sides. And so what we get from that is we have dV dt is equal to 1 over the capacitance. Okay. The capacitance is usually a constant, so we usually don't assume that changes with time. Okay. And so the time derivative on the right gets passed to the charge. And the time derivative of electric charge is equal to the current. Okay. And so our final formula here is dV dt is equal to I, the current, divided by C, the capacitance. Okay. All right. So let's take this result and let's use our analogy. Right. So we have our analogy for the voltage in a circuit. We have our analogy for the current. Okay. The capacitance, we're gonna leave it on its own. So we're just gonna leave it as the capacitance. Okay? And so our LPM equation here is we have dP dt. Okay? So this dP dt here represents a change in pressure on the capacitor. This is equal to 1 over C. Okay. The capacitance is still the capacitance. Right? And then we have the analogy for the current, which is our volumetric flow rate, which unfortunately has the same symbol as electric charge, which is Q. Okay. This Q here is the volumetric flow rate. All right. Any questions on this so far? Okay. All right, so a little bit of trivia on the capacitance. Okay. What the formula there is telling you is that the time derivative of the pressure depends on the capacitance. Okay. And so basically, what this tells you is that high values of capacitance, okay, and a high value of capacitance basically means that your blood vessel walls are very flexible. Okay. What that tells you is that this is going to dampen or kind of dull out any rapid changes in pressure. So even if you're in a situation where pressure wants to rapidly change, so let's say that you're near the heart, the fact that you have flexible walls basically prevents that pressure from spiking too quickly. Okay? So another way that you can think about it is that the capacitance or the vessel wall flexibility places a cap on how quickly the pressure can change. So when we're doing modeling for the larger vessels, the capacitance is a really important property to account for. Okay. All right. Another piece of trivia. Sometimes you'll hear me say this, and today that's actually been pretty good. But capacitance is kind of very much like an electric circuit type of word, and so for fluid mechanics and for blood flow, we've adopted another word for it. And so instead of capacitance, we often use the term compliance instead. So sometimes you'll hear me use the word compliance, and so when I say compliance, that's just the same thing as capacitance. And so just an FYI. Okay, so that's compliance or capacitance. Okay. The last circuit element that we're going to go over are the inductors. Okay. And so if you look at kind of our two circuit elements so far, we know that resistors represent viscous resistance or viscous friction, and we know that the capacitor represents the flexibility of the vessel walls. Okay. Inductors represent kind of the third kind of main fluid mechanical property that we need, which is inertia. So we talked about inertia quite a bit when we talked about our fluid mechanics review. Okay, inertia comes from the fact that all blood or all fluids have mass, right? Okay. And just like anything with mass, it's going to resist changes in its motion. Okay. That goes for anything, right? And so if you have something that has mass, and so let's say we have that bottle of hand sanitizer, right? If I were to push it, it would take a while for me to yeet it off the table because that thing has mass, right? It would take a lot of force and some time. So same thing with blood flow, right? And so you can't take like a pipe flow and expose it to a pressure difference and expect it to accelerate to max speed right away. Okay. Okay. And so, thankfully, electric circuits have the same kind of phenomenon, right? And that's through inductors. Okay. And so an inductor is often represented by a coil. Okay. Not to be confused with a resistor. So a resistor is a kind of a sharp squiggly. An inductor is a curvy squiggly. Okay, so I'm just going to jump, I'm just going to jump straight to the fluid mechanic equation here, just because I want to make sure I get through this today. And so if we have an inductor and it's exposed to a pressure difference P1, P2, okay, right? And our inductor has a value L. If P1 is greater than P2, right? So we have a pressure difference in our blood vessel. This is going to accelerate flow, so it's going to cause flow to go from left to right. Okay. So that's true. So that's not going to change, right? And so, whenever you have a positive pressure difference in your blood in your pipes, it's going to cause fluid to flow. Okay. All the inductor basically says is that instead of going from 0 to 100 right away, there's going to be some ramp up period. Okay. Okay. So the formula for the inductor is the following. And again, I'm just jumping straight to the fluid mechanics version. So we have dq dt. Okay. So dq dt obviously represents the change in the flow. Okay. Okay. This is equal to 1 over the inductance, 1 over L, multiplied by the difference in the pressure. So multiplied by P1 minus P2. So this L here is the inductance. And this P1 minus T2 is obviously the pressure difference. All right. Any questions on this so far?
Is capacitance and inductance the values that are just kind of like given, like almost like material properties, or is it like something you have to solve for, like resistance?
Yeah, great question. I was actually going to get to that next too. So for the resistance, we did have an equation for this. And so, based on fluid mechanics, based on Navier-Stokes, we can compute roughly the resistance of a blood vessel using this equation here. For capacitors and inductors, these technically in theory, you could compute these, okay? Right? Because in theory, capacitors and inductors, they do represent physical traits or physical properties of the blood vessels themselves, okay? Because these circuit elements do represent physical things, and so you should be able to compute their properties using physical quantities, right? In theory, of course, and of course, I have the caveat there because it's not always as easy as it seems, right? We were able to come up with an equation for the resistance because it's pretty clear from the Navier-Stokes equations, right? And if you remember, we had to make a lot of assumptions along the way. So we had to assume that the flow was steady, that the flow was had rigid walls, right? So there's a lot of assumptions that came into that. Once you start to get into capacitance and inductance, you start to get into more complicated fluid mechanics, right? At the very least, capacitance and inductance are only phenomena that you observe when the flow is unsteady. Okay? So that already kind of makes it really difficult, at least to take the same approach that we did with the resistance, right? So we can't just, so it's a lot harder to look at the unsteady Navier-Stokes equations and kind of derive an expression for the capacitance and the inductance from that, okay? Even more specifically though, for the capacitance is actually very difficult, or I should say compliance. Okay. Because I try to say capacitance and compliance at the same time. So capacitance relies a lot on the material properties of the vessel wall itself. And so that includes things like the Young's modulus, that includes things like the Poisson's ratio, bulk moduli, things like that. And the thing with biological tissue is that we understand the material properties of these biological tissues a lot less than we do, say, like an earth material, like a metals and things like that, right? So that makes it even more challenging to get a value for the compliance. Right? For the inductance has the challenge of it being mostly an unsteady kind of fluid type phenomenon, and so the inductance is also reliant on things like flow patterns and velocity of field and things like that. And inductance also is affected by turbulence as well in some cases. Okay. I know I've already mentioned in the class that, you know, blood flow isn't exactly turbulent, but you do still see sometimes some transient small turbulent effects, and that affects things like the inertia. Okay. And so and so with all these factors combined, you know, it is very difficult to come up with kind of an explicit equation for the capacitance and inductance. People have tried. I've seen some textbooks and some papers that have tried to do it, but you know, honestly, the results aren't that great. They're not as ubiquitous as the resistance equations. Okay. And so, you know, if that's the case, you know, how is this useful to us then? If we can't even determine the values of these parameters, you know, is this even, you know, a thing? So to set these parameter values, and to an extent, this applies to the resistance as well, right? Because remember, the resistance equation that we have, you know, it depended on rigid walls and steady flow, which, you know, which obviously, you know, sometimes we don't, or a lot of times we don't assume that. Okay. We're going to go through a process called parameter tuning. Where it's almost like kind of an opposite approach to setting parameters where, you know, I think for a lot of people, you know, a lot of people are used to what's called forward modeling, where, you know, you have your equations, you have your parameters, and you set their values before you even start solving the equation, right? And so after you solve the equation, you get your solution. Okay. With parameter tuning is a form of what's called inverse modeling. Inverse modeling is a very fancy way of just guess and check, right? And so in inverse modeling or parameter tuning, what we're going to do is we're going to run our LPM, okay? We're going to look at our results, and then based on our results, based on kind of what we expect for the blood pressure, what we expect for the flow rate, what we expect for the heart rate, things like that, we're going to tweak the parameter values until we achieve what we want, okay? So it's a very kind of iterative process. It's literally just kind of guess and check, right? You know, I guess that's a little bit too simple. So, you know, it's like an educated guess and check. It's a guess and evaluate, I guess I should say, right? And so we're gonna go through that in depth probably on Thursday. So, yeah, the issue of determining these parameters is a big deal, and in fact, actually a big portion of my doctoral thesis work actually went into parameter tuning. So, and it's still an issue. Okay, any questions on this so far? Okay, all right. So we have about 6 more minutes left in class, and so I'm just going to introduce the next thing. We're going to spend most of the time on Thursday talking about this. So today, you know, today we didn't really do any problems. We just kind of introduced the idea of LPM. We talked about the kind of the theory and kind of the representation of the different elements. Okay. Thursday, we're actually going to start to do some work, some forming equations, solving equations, doing things like tuning. Okay. Okay. So we're going to start with deriving LPM equations. Okay. All right. So what I mean by this, by deriving LPM equations is, you know, oftentimes, you know, when you seek to model a blood vessel using lump parameter modeling, you're going to represent it using a circuit. Okay? And so once you kind of determine your circuit, the next step is to kind of generate the equations that govern that circuit. So when I say deriving the LPM equation, this means that basically you take a circuit and you generate or you derive the equations that govern that circuit. Okay. All right. Because what we have so far, so we've introduced the different elements, right? Each of those elements is governed by a different equation, but in reality, when you kind of put them all together, you put them all together in a circuit, they're all going to interact and they're all going to share different variables. And so being able to take a circuit and govern its or derive its equations is a really important skill. And in fact, it's going to make up the bulk of your next homework assignment after this tutorial is done. Okay. Okay. So let's start an example. I know we're not going to be able to finish it today, but let's at least start it so we can kind of start hit the ground running on Thursday. Okay. Let's do a very simple circuit and let's talk about how we derive its equations. So let's start with a simple RC circuit. Okay. So a circuit that is comprised of a resistance and a capacitance. Okay. We're going to put them in parallel. So they're going to look like this. Okay. We have one resistor. We have one capacitor. Okay. This little symbol that I put at the end here, this is called ground. So ground is simply just a reference point. Okay. And for our purposes, we're going to assume that ground has a pressure of 0. Okay. That's going to be relevant in a second. All right. And so this simple RC, right, this resistance capacitance circuit, in fluid mechanics, this is what's called a 2-element Windkessel model. Okay. Because if you think back to the Windkessel model that we talked about in the beginning of class today, right? A Windkessel model is comprised of a flexible chamber, right? That's represented by the capacitance or the compliance, and it's also represented by your highly viscous outflow channel, which is given by your resistance here. Okay, and of course we need our pump, and so our pump is going to be given as an inflow boundary condition, and so we're going to say that we have QT, Q of T. So this Q of T here is our inflow boundary condition. And then at this junction right here, we have a pressure. Okay. All right. And so, just to kind of refresh your memory on kind of basic circuits, if 2 points are connected by a simple wire, we're going to assume that they have the same voltage, or in other words, in our case, the same pressure. Okay. All right, and so the process of deriving these equations, we're going to use Kirchhoff's current laws, or Kirchhoff circuit laws. I always spell his name wrong. Okay. So when we come back on Thursday, we'll pick up this example. In this case, we're going to use Kirchhoff's current law together with the equation for the capacitance and the resistance to get our one ordinary differential equation that governs this circuit. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. So that's all we got time for today. So Thursday we'll pick this up here. Remember to be if you haven't started yet, remember to start your Vascular tutorial You know, come and ask for help if you run into issues. And so if anything, just from, if you will just want me to look at your model and just get interested for me to give you feedback, I can do that too. So don't be afraid to come ask, right? So thank you guys for coming today. Hope you guys enjoy the rest of your day, and I will see you on Thursday. Yeah.
So, I hope, I file.
Okay. Yeah, so you need to, so same thing over here too. So you need to, let me see for a second. So you need to leave the segmentations that actually go inside the channel.
If it's a, I tried. All you got, you gotta be like. Yeah, you got it. Do that. Oh, yeah.
Okay. So you need to extend your path.
Yeah.
Whenever you make a.
So one more point.
The only thing we took out.
You need to, so you might have to remake the path. So you need to. Starting to have when you start.
Oh, the manual.
Exactly.
Okay.
So that's true for any investment, but you make sure you, otherwise it's really hard to remove the segmentation.
Okay.
So I'd say that's the appropriate.
Yeah, so we, get more patch on,
Yeah, add more, see, I don't know if they changed it, but before it was always really hard. So if you want to add a point, because your path,
Like we could get
path is this one.
something
So
bad.
I've always thought it'd be hard, or for me personally, using the past resolution boundaries and should add a point kind of at the beginning here.
Yeah.
So that's essentially what you want to add a point in here, so that it kind of continues from there. But usually when you add. I don't know, I haven't tried this add menu, but here, I don't know if there's a menu. But you want to make sure that you have a.
yeah, we start from the main one.
Exactly. Okay. Yeah. So start with that.
Yeah, so I have to keep it.
Yeah.
And then you want to leave file and we shot it back.
Yeah.
I just wanted to show what I have right now.
Sure.
So this is what I have. I only have a screenshot because I have it on my PC at home.
Okay.
The Mac one, it's kind of weird because it's on a white text on a white background.
Oh,
So
yeah, a lot of people have been having issues with the.
that's how I just use my PC instead.
Yeah, I
of
know.
watching,
It's a little hard for me to see, but I'm like, I mean, just same thing I was telling Kevin too, is a lot of things I'm looking at is the junctions with the branching goes. I can't really tell right here, but it looks like your vessel's coming out okay, so it looks like you have that one segmentation right here. And it looks like there's another one on the other side, that's kind of what it is. That looks
Not
okay.
hard.
When you count the number of samples, you get.
I don't know.
But I would double check that. This one looks great. This one coming off. Really, I can tell that it's kind of starting here. I would just double check the number of samples to make sure that it's fine. Overall, this looks pretty good. The only feedback I would say is that, you know, because of the way that the Sebastian makes the model, it basically tries to connect one segmentation to the next one.
Yeah.
And so if you have a situation where your segmentation is kind of rapidly changing direction, like kind of like right here, you can like trying to kind of make this. Kind of
It goes out and then it.
So create kind of like a drag.
The one on the right.
I would be able to clean that up a little, either try to move the
The way
segmentation.
it's bodies, the kitty.
Sometimes it's hard just based on the trajectory. So you have to find a good place.
Yeah.
But you want to, but you always want to try to make it so that your segmentations are always kind of like nice and even and smooth like this.
Okay.
That is hard to do when the vessel is making turns, but you know, I think right here you did a really nice job.
Okay.
You're making this turn right here that's kind of nice and smooth. So if you kind of like clean up some areas like this to make it more like this. I think that would be-
Alright. Thank you.
Yeah.
I just wanted to show you my.
Sure. Uh-huh.
I was having trouble with this one, but I know the way it goes kind of down.
Yeah, yeah.
And I didn't, the structure looked like set 5, so I didn't picture on.
Okay. Oh, that's fine. More practice. Your midterm project, it's actually gonna have more than that, so, you know, more practice.
Yeah.
Okay.
I think it's just getting used to it.
Yeah. Alright, so same thing I was telling him too, that, when Sebastian makes your model, basically, the next segmentation,
Have to shut down the whole software and then reopen it and then let me.
We have kind of like,
Yeah.
it's a little bit pixelated here, but it goes on time, like there's like some kind of problems.
Yeah.
Like the segmentation kind of did this and then
I kind of got lost with that.
yeah. So sometimes, you know, you have to be a little bit strategic about where you put the segmentations, because if you put them, you know, if you put them in fixed intervals, like you put them in 10 slices each time, you could end up in situations like this.
Yeah, cause I started going, I think I was doing like 10.
Yeah.
I was doing 20, like you were just for the original, and then I started doing 10, and then for the small ones, I was doing 3.
Yeah.
Cause I wanted
Yeah.
to get like finer point, cause yeah, some of them were like broken, like.
Yeah.
It'd be 1 point here and 1 point, or 1 plane here, 1 plane there, and it's like, it comes out like squished.
Yeah, yeah, so you wanna be a little bit strategic on how you space the segmentations. Granted, sometimes there's not much you can do just because of the.
Yeah, that one, I think I did it
Um,
like 4 times, cause I was trying to get like.
Yeah,
feel
yeah.
like that.
But you want it to be kind of smooth, because like this, something like this looks great right here.
Yeah.
Like, this is really nice and smooth. I would check this out to make sure. It looks to me like there's one segmentation that's kind of, you're kind of catching kind of this part of the vessel right here too.
Yeah, cause I was saying like, in terms of the cuts, when we do the threshold,
Yeah,
it would just probably just shrink this more, right? It's probably
Yeah.
taking account for a whole part.
yeah. So one thing I forgot to mention in the tutorial is that you're not just limited to just the threshold tool.
Mhm.
So there's other tools where you can just draw like a manual circle. And so you can use that too. In
Oh,
some
okay.
situations where you're kind of at a weird cross section, you can use like a circle. Or you can copy and paste too, so you can copy a segmentation, like the one down here goes great,
Yeah.
and so you just copy and paste into that spot right there, just so you have a nice smooth. It looks like your vessels are coming off okay, so I don't see, you know, did you check the number of caps you should, because you have 5 vessels, so you should have 6 caps. So when you make your model, so when you hit this model tab right here, oh, you should just be making one model file. So you should just be one, and you just add all the segmentations.
Oh.
Yeah, and then from there, you can check the number of caps. And so the number of caps for you is 6, but you have 6. Number of vessels.
Oh,
So right now we said delete all the model array and get the one.
Exactly. Yeah, so for you, because your models aren't fully connected, I think you're gonna have more caps.
Yeah.
Because the cap, basically, the master takes the ends of your vessel and turns them into.
Oh.
And so give a vessel that's kind of like, mostly branching off, but if it's like sticking out a little bit, it's gonna create another cap.
so kind of with these that have different models, like what's that would be here.
Exactly.
Oh,
Yeah, yeah.
so I just basically just delete all this, delete all the models. Single.
Yeah. Okay, yeah, I think for you, it should be okay, because it looks like all your vessels are coming off okay.
Yeah.
But I think for yours, I think you'll have extra caps, because your vessels aren't fully connected.
Yeah, so I have to create more path.
Exactly.
Yeah, stop with
Is
that.
it fine if I do like that, or I go back and do like the models?
So, I mean, for this, it doesn't matter, but it's
For our like actual.
for your actual model.
Okay.
Yeah, I mean, because visually that would look like all the branching that would come up. So I would.
Oh, okay. That's all I make sure.
So just the picture on the PDF, that's it, and then the
the
file.
Exactly, yeah.
So what? Thank you very much, Professor.
Of course.
And sometimes when I create a model,
Uh-huh.
it's saying give me error because I think because when I create a segment, it's gonna overlap.
Yeah, so if they're overlapped, you have to kind of, space them out so that they're not.
Oh, okay.
overlapped. Yeah.
Thank you very much.
Yep.